This lecture is on significant digits, along with some scientific notation and rounding. We need to make sure we can identify the significant digits in a number, scientific notation or standard notation, and round the number successfully. Let's give an example of how significant digits and uncertainty affect numbers and calculations. So I thought of this example with a bakery. Maybe an owner of a bakery chain said that they needed 2,478 kilograms of flour every week. A number like this, you would probably assume that someone had calculated to within the closest kilogram how many kilograms are needed. So this is plus or minus 1 kilogram. This we're not sure. Is it 2,500 plus or minus 1 kilogram? Is that where the uncertainty is? Or is the person just telling you 2,500 kilograms just to let you know that it's somewhere between 2,400 and 2,600 kilograms? That is, it's plus or minus 100 kilograms. If you knew how many kilograms per cake, let's say that it took 0.416 kilograms for every cake that you make, then if you know one of these numbers, plus or minus 1 kilogram, you can be a lot more certain of the amount of cakes you can make than if it's this number that's plus or minus 100 kilogram. That's a pretty big uncertainty in the amount of cakes that you can make. And significant digits are a way that we can express the uncertainty in a measurement or in a calculated value or in any number that you're working with. We already mentioned a little bit of Section 2.1 in the previous lecture on measurement, and we did mention significant digits, saying that the last significant digit is where the uncertainty in the measurement is. So let's take a closer look at what significant digits are. Sometimes they're called significant figures. Even I go back and forth between these two terms. So significant digits or significant figures. So in the example we were talking about before, when you have all non-zero digits, it's pretty easy to determine that all of these are significant. This is where the uncertainty is, plus or minus 1 kilogram, because all non-zero digits are going to be significant. So all of these are significant. This number has 4 significant digits. The problem comes when you have some zeros. Do these zeros mean data? Are they counting the actual kilograms that you need, or are they just placeholders letting you know that it's 2,500, not 250, not 25? So in numbers, zeros can help hold the place value and let you know what value you're talking about. So zeros serve two functions, and we have to determine when they are serving the function that they are expressing data and when they're just serving the function that they're telling you where to put the decimal point in this number. And the rules for determining whether a zero is significant or not is that the zeros that are to the left of non-zero digits are never significant. So a number like this, these zeros are just holding the decimal point where it needs to be. It's not 4.5 grams, it's not 45 grams, it's 0.0045 grams. So these leading zeros are not significant. They're never significant. So this number would have 2 significant digits. Zeros in between non-zero digits are always significant. So if you have a number 405 kilograms, you can tell that this was counted to the closest kilogram. And so this zero means something. It's not supposed to be a 1. It's not supposed to be a 9. We know that we have 405 kilograms. So we have 3 significant digits. Zeros to the right of the non-zero digits. Some people get confused. It's not to the right of the decimal, it's to the right of the non-zero digits. The zeros to the right of the non-zero digits depends whether there is a decimal in the number or not. So our example up here, 2,500 kilograms, these are to the right of the non-zero digits. Here's the non-zero digits, and these zeros are to the right. and there is no decimal in the number. So these are not significant. This would have 2 significant digits. If we wrote the number with a decimal, we could show that these zeros are significant. So now these zeros, still to the right of the non-zero digits, they're still to the right, but since the number has a decimal, now these are significant. So 2,500 written with a decimal would have 4 significant digits. These also are to the right of the non-zero digits. So these zeros would be significant. And if we wrote it as a decimal with another 0 after the decimal, we would have 5 significant digits. So written like this, with the 2 significant digits, we are implying that this number is plus or minus 100 kilograms. This one, with 4 significant digits, makes this 0 the last significant digit. We are implying that this number is plus or minus 1 kilogram. And this value of 2,500 written with a decimal and another 0 after the decimal, having 5 significant digits, implies that this measurement is plus or minus 0.1 kilograms. I just wanted to briefly make a note about rounding numbers. Some people have questions on that. If you were supposed to get paid $100 and the check said this, 100.0, that would be a little bit weird, but you wouldn't really mind it so much. If it said just 100, either with or without the decimal, you wouldn't mind so much. If instead the check said just this or just this, you would have a little bit of a problem, because when you start chopping off zeros that are to the left of a decimal point, you start changing the meaning of the number. So digits to the left of the decimal point can't be chopped off. Digits to the right of the decimal, when you're looking at significant digits, they must be chopped off. Because even though these have the same numerical value, remember they have different number of significant digits. This number here would have 5 significant digits. This number here would have 4 significant digits. This number here would have 1 significant digit. So we are changing the number of significant digits. For that reason, the digits to the right of the decimal should be chopped off. So let's go ahead and round this number, 5,681.5982. Let's round that to 7 significant digits. Right now it has 8 significant digits. All of these are non-zero numbers. It's pretty easy. And we want to make it 7 significant digits. So that means we want to keep these first 7 and we want to lose this 1. When we lose that 2, it's a small number, so this 8 is going to stay the same. It's not going to bump up to 9. And that 2 is just going to go away. It's not going to become a 0. If it became a 0, we would still have 8 significant digits. We want 7 significant digits, so we want that digit gone. So now we want this 8 to be gone. Since it's a large number, we need to bump up the 9. When we bump up the 9, it actually ends up carrying over to the 5. So 59 becomes 60. And here we have our number with 6 significant digits. We don't have any more zeros here, because if we did, we'd have 7 or 8 significant digits. So this is the proper way to round to 6 significant digits. 5 significant digits means we're getting rid of the 9, which is large, so we're making this 5 a 6. If we're rounding to 4 significant digits, that means that we are rounding to this place value. We want to get rid of the 5, which is large, so we are making this 5,682. For 3 significant digits, we want to round it to this place, the 8. The 1 is small, so we're going to keep the 8, but now we're starting to chop off digits that are to the left of the decimal point, and we can't just get rid of them. We have to use a placeholder 0 and no decimal point, because a decimal point would make it 4 significant digits. With 2 significant digits, We are rounding to the 6th place. The 8 is large, so we're making this a 7. Again, keeping placeholder zeros. And if we only wanted one significant digit, we would make this 6,000 with 3 placeholder zeros. I am going to go ahead and leave these for you to practice and either look at the answer key or look at the additional video that I've made posted next to the answer keys. I want to mention some scientific notation, especially regarding significant digits. In scientific notation, our numbers are expressed as a term, also called a coefficient, or a mantissa, or significand, and the base and the exponent. So we have a power of 10 in addition to this term. The term should be between 1 and 10, so there should be a decimal between the first and second digits. You should not write this as 46.8 or as 0.468. Those would not be correct. So let's start with this positive power of 10 first. 10 to the 4 equals 10 times 10 times 10 times 10, which equals 10,000. And so 2.1 times 10 to the 4 grams equals 2.1 times 10,000 grams, which equals 21,000 grams. So another way to do this is to make the number bigger by 4 place values, 4 powers of 10. So we're making the number bigger by moving the decimal to the right, 1, 2, 3, 4, and then we add in some placeholder zeros. Notice that in the original scientific notation number, we did not need placeholder zeros because the place where the decimal belongs is being told to us by the power of 10. And so any zeros that you show in the term of a scientific notation number, you're showing because they are significant digits. That makes the significant digits for scientific notation extra easy. Anything you see in the term has to be significant because we don't need placeholder zeros. Let's remind ourselves what a negative exponent means. 10 to the 3 is actually 1 over 10 to the 3. That's what that means. And so that is 1 over 10 times 10 times 10, which is 1 over 1,000, which equals 0.001. So this scientific notation number here, 4.68 times 10 to the negative 3, is equal to 4.68 times 0.001 liters, which equals 0.00468 liters. Another way to do this is to make it smaller by 3 orders of magnitude, 3 place values. So we're making it smaller by moving the decimal to the left. 1, 2, 3, this is where the decimal is going to go. And then if you just want to put 0.00468, that's okay. If you like putting another 0 in front, that's okay too. All right, I'll just go ahead and do one of each of these problems, and then the rest will be in the answer key and supplementary videos. So 4.7 times 10 to the 6th, we're making that bigger by 6 orders of magnitude. So this would be 4,700,000 as that number. So 1, 2, 3, 4, 5, 6 places is where the decimal was moved to. This one is made smaller by 2 orders of magnitude. Usually when we make the number smaller, we're going to have to put the decimal there. When you make the number larger like this, it's best not to put the decimal point there because we have a special meaning when some number has a decimal point. That means that the zeros to the right are significant. Since this number only has 2 significant digits, then we should write the standard number with just 2 significant digits. We should not write this as 4,700,000 with a decimal point, because this, with the decimal point, now has 7 significant digits. And that is not correct. When you are multiplying two numbers that have an exponent, two of the same number, x to the 6 times x to the 2, or 10 to the 6 times 10 to the 2, we're going to add the exponents. So this would be 10 to the 8th. When we are dividing, we are going to subtract. 2 minus 4 equals negative 2. So this equals 10 to the negative 2. Let's try converting this to scientific notation. We have to make this into a term that has the decimal between the first two digits, so a number between 1 and 10. We're starting with a number that is not between 1 and 10, and we're changing it so that it is between 1 and 10. To do that, we had to make this number smaller, and so to counteract that, we need a positive exponent. If you get confused whether the exponent should be positive or negative, then you can try going the opposite way. How would we convert this to a standard number? And it would be 654. If you had put a negative 2 by accident, then when you converted it back to a regular number, you would see your mistake. This one's a little bit different because it already has a power of 10. Let's go ahead and convert this first. So 0.0022 is the same as 2.2 times 10 to the negative 3. So if we have 2.2 times 10 to the negative 3 times 10 to the 5, then this would equal 2.2 times 10 to the 2. And if you like, you can double check this by converting both the original way it was written and the scientific notation to a standard number, and you get 220 for both of these answers. So you know that these two are equal. Hopefully you can get to a point where you're comfortable using your calculator to do scientific notation calculations, but it's helpful to be able to do mental math on scientific notation. You can use that to double check your results or see when something is completely unreasonable in your calculator. So here we have 2.5 times 10 to the 3 times 4.0 times 10 to the negative 1. So we can rearrange these, and we can have 2.5 times 4.0 times 10 to the 3 times 10 to the negative 1. And 2.5 times 4 is 10. 10 to the 3 times 10 to the negative 1 is 10 to the 2. And 10 times 10 to the 2 is the same as 1 times 10 to the 3, which is the same as 1,000. We can separate the terms, 3 divided by 6, and we can separate the exponents, 10 to the 4 divided by 10 to the 6. 3 over 6 is the same as 1/2, or 0.5. So we have 0.5 over here. 10 to the 4 over 10 to the 6 is 10 to the negative 2. And this is the same as 5 times 10 to the negative 3. So in case that was a little fast for you, remember before we had some numbers where the term is not written correctly. 0.5 times 10 to the negative 2 is not a correct scientific notation because we need to have this first term with the decimal between the first and second digits, or we need a number between 1 and 10. So 0.5 in scientific notation is 5 times 10 to the negative 1. That would be the correct way to write 0.5 in scientific notation. And then when we carry down the 10 to the negative 2, then that gives us 5 times 10 to the negative 3. So that is how I got this result over here. When we do these conversions back and forth, to scientific notation, we have to make sure that we are keeping the correct number of significant digits. So let's go ahead and tell the correct number of significant digits and convert it to scientific notation correctly. I'll go ahead and do all of these. So hopefully you can see that this 0 here is to the right of the non-zero digits, and there is a decimal in the number, so it is significant. We have 4 significant digits in our standard number. When we convert it to scientific notation, we're going to keep that significant 0 so that we still have 4 significant digits, and then that would be 10 to the 1 grams. This one here, our leading zeros are never significant. To the left of the non-zero digits are never significant. This number has 3 significant digits. This 0 in between is always significant. So we are going to keep 3.04 times 10 to the negative 2 kilograms. These numbers are significant. We have 5 significant digits. We're going to keep all 5 here. When we convert to 7.000 times 10 to the 1 milliliters. These ones are not significant, so we are just going to keep 1 significant digit, 2 times 10 to the 2 meters. This one in between is significant, so there are 3 significant digits here. We're going to keep all 3 when we convert it. 3.07 times 10 to the 1 degrees Celsius. These are not significant, but this one is. So this number has 3 significant digits. We're going to keep 3 significant digits when we convert it to scientific notation. So we have 5.60 times 10 to the negative 4 liters.